Hi, everybody. Welcome. I'm Irit Dinur, a faculty at the School of Math, and I have the pleasure of introducing our public lecture speaker for today, Professor Tim Roughgarden. Um, Tim graduated from Cornell in 2002 and then spent a couple of years as a postdoc in Berkeley, where we had a shared office for a little bit. He then moved to become a faculty at Stanford, and in 2019 joined Columbia University as a professor of computer science. Tim is a real scientific leader in algorithmic game theory, which is at the intersection of economics and computer science. And one of Tim's most celebrated works is a paper called How Bad is Selfish Routing? This gives a quantitative analysis of a paradox called Braess's paradox that tells you that sometimes when you build a road, you actually cause more congestion than you had before. And Tim's work somehow explains qualitatively how bad that is. That paper went on to win a very prestigious Gödel Prize named in honor of Kurt Gödel, who himself was a faculty here at IAS in the School of Math for many years. And Tim later received a Guggenheim Fellowship and the 2016 Kalai Prize as well. Beyond the algorithmic game theory, Tim has a wide-ranging outlook. He has written several excellent books and many surveys on a broad collection of topics in computer science. And even just a couple of days ago on Monday, he delivered a really beautiful talk in the mathematics colloquium on a different topic called Beyond Worst Case Analysis. And I look forward very much to hearing Tim's talk today. So please join me in welcoming Tim.
All right, thanks everyone. Sound is okay? Volume's okay back there? Great. So good evening. Thanks so much for spending an hour with me. The plan for today is I'd like to introduce you to a few of the several points of contact between two fields. On the one hand, computer science, especially theoretical computer science, and on the other hand, game theory and economics. And you know, if you're giving a talk at the Institute for Advanced Study, and you're going to talk about computer science, and you're going to talk about game theory, there's kind of only one way you could possibly start your talk, which is with a photo of John von Neumann, who of course was completely essential for the origins of both of these fields. Game theory, he'd already laid most of the foundations in the 1920s, like his famous min-max theorem, but game theory really started to have a big influence, really started to go viral with his 1944 book authored with Oscar Morgenstern. And amazingly, that was kind of like almost exactly the same time when von Neumann was contributing to the very first efforts to build general purpose computing devices. First as a consultant on the ENIAC project, and then of course leading the effort here at IAS. I think initially in the basement of Fold Hall. I just learned from Aaron before this talk that like it moved into the building that's now the preschool, which I don't know, it's like kind of cool, I think. So anyway, it's pretty remarkable CV doing both of these two things. As far as I know, he never tried to combine these two sort of lines of effort. And indeed, as the 20th century unfolded, computer science and game theory just sort of evolved largely independently with very little communication between them. That's a huge contrast to the 21st century, where there's been a very lively conversation between the two fields, which is what I want to tell you about today. But before I get to the 21st century, let's spend a little more time in the 20th, and let's talk about sort of one revolutionary idea from each of these two fields. Let's start with game theory, and let's talk about Nash's theorem, right? Which in some sense, theorem proved in 1950 here, at Princeton, which gave game theorists and economic analysts, in some sense, everything they could possibly want. In the sense that Nash's theorem tells you any strategic situation, okay? Doesn't matter who the decision makers are, doesn't matter who the actors are, doesn't matter what they can do, doesn't matter what they want. With no assumptions whatsoever, it is guaranteed to possess what Nash called an equilibrium point, what we would today call a Nash equilibrium. So what's an equilibrium? Well, I think most of us have kind of a good intuitive sense of what an equilibrium is just from practical experience. It's sort of everything is settled into an outcome where any given actor doesn't want to change what they're doing given what everybody else is doing. Okay, so it's a Nash equilibrium. It's an outcome of a game where everybody is doing the best that they can given the actions chosen by everybody else. Hopefully, Nobody in this room thinks they know what a Nash equilibrium is because they watched the movie A Beautiful Mind, which came out in the 1990s. The key scene of that movie that purports to explain what a Nash equilibrium is actually gets it completely wrong. So if you've ever seen that scene, please wipe it from your memory. Probably the easiest way to get a feel for games and Nash equilibria is to look at some examples. So you can think about the game of chicken. Okay, so two people driving cars at each other at full speed. You can either keep driving or you can chicken out and swerve. Okay, and you want to win. You don't want to get into an accident. That'd obviously be bad. But subject to not getting into an accident, you'd like to win in the sense that you'd like to go straight while the other player chickens out and swerves. So you can encode that as a 2x2 matrix. The rows here correspond to the first driver's possible actions. The columns here correspond to the second driver's possible actions. And in each entry of this matrix, I've sort of shown you the row and column players respectively payoffs, with higher payoffs being better. So an accident's bad, they get negative payoffs. If you don't get in an accident, you get at least 0, and if you were the one that won the game, then you actually get a payoff of 1. So that would be one way to encode the game of chicken into game theory formalism, okay? Not hard to see there are equilibrium points of the chicken game. So for example, if the first driver chickens out, but the second driver goes straight, that's going to be an equilibrium. Certainly the second player is happy because they won the game. But if you think about it, the first driver, given that the other player is going straight, the best action, the best response for the first player is indeed to chicken out. Because if they didn't, if they also went straight, they would wind up in an accident, which would be even worse. And there's also a second equilibrium with the roles of the two players reversed. Another familiar example, rock, paper, scissors, or Rochambeau. Okay, so now each player, still two players, but now each one has 3 actions, hence the 3x3 matrix, right? If you pick the same, I'm sure you all know the rules, right? Rock sort of breaks scissors, scissors cuts paper, paper covers rock. So this is the tie where they choose the same action, and then here, whichever player wins gets a payoff of 1, and whichever player loses gets a payoff of -1. And when you see the rock, paper, scissors example, you may have trouble reconciling this with what I said earlier about Nash's theorem saying that every single game has a Nash equilibrium. Because if you think of any of these 9 outcomes, none of them actually are in equilibrium. It's not the case that both players are happy in any of these outcomes, right? So like if you're the first player and you play scissors and you're getting smashed by rock, you definitely don't want to stay here. You want to switch to paper so that you can cover rock. And same thing for the other 8 outcomes. So the twist, and one thing you should really know about Nash equilibria, is players are allowed to randomize. That is, you're allowed to flip coins in your head, in effect, and the outcomes of those coin flips can dictate what action you play, okay? So then, if you allow randomization, there is indeed an equilibrium, in fact, a unique equilibrium of rock, paper, scissors, where each of the 2 players chooses one of their 3 strategies uniformly at random. Okay? Why is that an equilibrium? It's because it guarantees that no matter what the other player is doing, you're equally likely to win or to lose or to tie. Okay? So that's rock, paper, scissors. Returning to the chicken game, I showed you the 2 equilibria before. Turns out there's actually a third in which players are randomizing. In this case, 50-50 between the 2 actions, which means at this equilibrium, there's actually a 25% chance that they get into an accident, which kind of seems weird. And I have to tell you, like, for most of my career, obviously I knew about this example and this mixed equilibrium, and I was like, okay, that's just kind of a mathematical artifact of the definition. That's not really real. And then I spent my last sabbatical in London, and I spent a lot of time like walking around London. And I don't know if it's because like in London you drive on the left, but a ton of the people that live there are from countries where you drive on the right, or what. But like walking on the streets of central London, I swear everybody's playing this mixed strategy. And believe me, I was in this square like every day. It was crazy, just bumping into people. It was weird. Anyways, game theory in real life, okay? So that's what I wanted to say about game theory for now. Let's switch over to computer science and also rewind a bit now to 1936. That was the year where Alan Turing published the paper that many of us computer scientists really view as the origin of our discipline. Right? And for that reason, many of us really feel that Alan Turing's name should be as household of a name as Albert Einstein. So what made Turing's paper so important? Okay, 2 things. So first of all, Turing proposed a formal, meaning mathematical, model of computation, a model we would now call a Turing machine. Okay, so we mathematically specified what it is that general purpose computing devices are capable of. Okay? Now, mind you, this is 1936. Remember the dates on the von Neumann slide, 10 years later. Okay, so Turing gives us a theory of computing before we actually have computing, at least in the modern sense of the word. Okay, already pretty amazing. Amazing thing number two, once you have the language to talk about what computers can do, you start to be able to contemplate what they can't do. And literally from day one of computer science as an academic discipline, we have known from Turing's work that there are problems that will never be solved by computer. Not in 2025, not in 3025, not ever. Problems that are called undecidable, fundamentally unsolvable by a computer, no matter what the technology. Some of these problems, quite natural, right? So for example, the halting problem, very simple. I give you some computer code. I give you maybe like 1,000 lines of Python, and you just want to know a very practical question, which is, could this program get into an infinite loop, or is it guaranteed to halt? And it seems simple enough. Maybe you just like run the program, see what happens, right? But think about it like, okay, so maybe it runs for 100 years. How do you know if it's in an infinite loop or whether it's going to finish tomorrow? You might hope there would be some simple shortcut to figure out which the answer is, but Turing's theory tells us that there isn't. You simply cannot tell even that simple problem. A couple pages of Python code, is it guaranteed to halt or not? Unsolvable by any computer, okay? So that's the work of Turing from 1936. Now I want to fast forward to the 21st century and tell you about 3 case studies of collaborations between computer science and game theory and economics, along with one digression along the way, okay? And the first case study, it concerns a model that Arit referred to. And on the one hand, it's a model near and dear to my heart. It's a model I was just completely obsessed over during my PhD. That's, I mean, even now, I think it serves as one of the most vivid illustrations of why computer scientists and economists really had to start talking to each other. So let's start with this, okay? This is going to be about routing in networks. When a computer scientist thinks about routing in networks, they're normally thinking of data flowing through a communication network. For this talk, feel free to think about something with which you're, I'm sure, all too familiar, which is vehicular traffic on roads. Okay, the principles are largely the same, okay? So let's start with an example, Pigou's example, very old example, over 100 years old. A.C. Pigou wrote about this in his book, The Economics of Welfare. So these days, I live in New York. I'm at Columbia University. For a lot of my career, I worked at Stanford. And for a chunk of those years, I lived in San Francisco. So I commuted from San Francisco to Stanford. And if you know the Bay Area at all, you know that there are 2 highways that connect San Francisco, which will be S in this example, to Stanford, which will be T. There's Highway 101 and there's Highway 280, okay? So which should you pick? Which should you drive on? Well, if it's the dead of night, if it's 4 in the morning, you always want to take Highway 101 just because it's shorter, okay? You'll get there faster. Middle of the day, less clear, because Highway 101 is more prone to congestion and traffic jams, okay? Unlike 280, which generally is always at the same speed, okay? So Pigou's example is a caricature of exactly that example. Again, think of this as San Francisco, think of this as Stanford. Each of the edges is annotated with what I'm going to call a cost function, describing the delay in hours suffered by traffic as a function of the fraction x of the traffic that chooses to drive on that edge. So this is a caricature of Highway 280, okay? Always takes an hour, doesn't matter if it's empty, doesn't matter if everybody's using it, always takes an hour. This is the caricature of Highway 101, where let's say that the delay in hours is equal to the fraction of traffic that chooses to use it. So if everybody uses Highway 101, it takes an hour. If half the traffic uses it, the traffic on Highway 101 gets there in 30 minutes, okay? So now I want to ask 2 questions. Question number 1 is, if you just let drivers do whatever they want, presumably trying to get to Stanford as quickly as possible, what do we expect to happen? What's the traffic pattern going to look like? Question number 2, if, hypothetically, we could coordinate everybody's route choices, could we do better? And if so, how much better? Okay. Let's start with question number 1. What do we expect self-interested drivers to do in this network? Well, I've set it up so it's actually a really easy question to answer. In game theory parlance, you would say that everybody has a dominant strategy. It's a dominant strategy to pick Highway 101 instead of 280. Why? The best case scenario, if you take 280, is that it takes an hour. The worst case scenario, if you take Highway 101, is that it takes an hour, okay, and it might be better. Okay, so it always makes sense to take Highway 101 in this example. And that means that at equilibrium, we expect to see everybody on Highway 101. And because of all that congestion, it's going to take them all 60 minutes to do the commute, okay, to get to Stanford. So that's question number one. Question number two, could we do better by coordinating route choices? And if you think for a minute, you kind of realize like pretty much anything would be better than the equilibrium. But if you really were kind of an altruistic dictator trying to just get people from San Francisco to Stanford as quickly as possible, what you'd do is you'd split the traffic 50-50, okay? It's true that the people routed on Highway 280 take 60 minutes to get there, but they were taking 60 minutes before, so they're no worse off. And meanwhile, the half of the traffic that's on Highway 101 now enjoys a relatively uncongested ride, and they get there in only 30 minutes. Okay, so on average now, the commute time has dropped from 60 minutes to 45. All right? So what do we learn from Pigu's example? Well, qualitatively, we learned something maybe we could have guessed, which is that if you just let people do whatever they want, act in their own self-interest, the outcome isn't necessarily the best one from a societal perspective, okay? And in economics parlance, you would say that the issue here is a congestion externality. The issue being that when an individual driver selects a route, they only think about the implications for themselves, their own delay. They do not take into account the fact that their presence makes everybody else a little bit slower, okay? So Koutsoupis and Papadimitriou proposed measuring the extent of the effects of these externalities, the extent to which self-interested behavior or equilibria leads you to outcomes not as good as optimal ones. And they proposed the term price of anarchy. And so this is a quantitative measure of this, which is the ratio between the commute time that you see at equilibrium and the best possible commute time if you could coordinate everybody's routes. So in Pigu's example, the price of anarchy would be the ratio between 60 and 45, also known as 4/3. Now, Pigu's example is not the most famous example of this routing model. That distinction belongs to what Arit referred to earlier, Braess's paradox, okay? So again, we have traffic going from an origin S to a destination T. There's again 2 routes available. Now both of the routes are basically the same though, okay? They have one edge, which always takes an hour, and they have one edge where the delay is proportional to the amount of congestion. So at equilibrium in this network, because these 2 routes are just kind of identical, you would expect the traffic to split 50-50, leading to an equilibrium where you have a commute time of 1.5 hours, right? 1 plus 0.5 here, 0.5 plus 1 here. Seems kind of boring. Doesn't really seem like a paradox. So to see the paradox, imagine that someone installs a teleportation device allowing traffic to go instantaneously from the midpoint of the top route down to the midpoint of the bottom route. Okay? And if you think about it, the traffic would be very excited to start using this teleporter. All right, so if you're the first driver that switches, for example, your commute time is going to drop from 1.5 what it was before to 0.5 plus 0 plus 0.5. It's going to drop to 60 minutes. Okay, if you were the only one to switch to using the teleporter. Of course, everybody's going to think just like you do. Everybody's going to switch to the zigzag path. The unique equilibrium in this network has everybody using the teleporter. And as a result, the upper left and lower right edges are now both fully congested, and it's somehow taking everybody 2 hours to get to work. Okay? And this is the paradox. Tried to be helpful, took this network, tried to speed people up by giving them a teleportation device, okay? And yet somehow the outcome is worse for everybody. Okay? You could ask, in the right network, is there any productive way? So again, suppose you had an altruistic dictator. Could you take advantage of that teleportation device in some way? And the answer is no. Okay, so it actually turns out that the commute time minimizing traffic pattern, even in the right network, is still the red traffic pattern. Which, if you think about it, means that the price of anarchy in this network on the right, again, the equilibrium commute time divided by the optimum commute time, is 120 over 90, also known as 4/3. More on the 4/3 coincidence, seeming coincidence, in a moment. Okay? So I don't want you to think that Braess's paradox is some artifact of some particular way you might sort of model traffic routing or something like this, because it's actually a fundamental phenomenon. And it shows up in lots of places, in lots of physical systems. For example, in mechanical networks of strings and springs. Okay? So you can take a bunch of springs, elastic, a bunch of inelastic strings, and you can tie them together just so. Okay? So you have a base fixed here. You have a string attached to another, sorry, a spring, two springs attached by a little tiny string. You hang a weight from below, stretching out the two springs. And then you add a couple seemingly redundant strings, okay, from the base to the top of the bottom spring and from the bottom of the top spring down to the weight, okay? So that's something you can just build. And now you can take a pair of scissors, and if you cut that little taut string in the middle, right, so you're chopping up this mechanical network, right? Presumably you're making it kind of only weaker. And yet, somehow, the weight rises further off of the ground. And there's a couple ways to see this. One way is just that the equations that govern the equilibrium of these physical networks are exactly the same ones that govern the equilibria of our traffic networks, okay? Where force corresponds to traffic, distance corresponds to latency, or sort of the travel time. The x's correspond to the elastic springs, and the 1s, 0s, and 1s correspond to the inelastic strings. So cutting this taut string here is doing nothing less than removing the teleportation device to recover the superior equilibrium traffic pattern in the network that we started with in Braess's paradox. If you prefer, you can also, in hindsight, convince yourself sort of directly why this would happen, which is that cutting this taut string basically frees up the two springs to carry the load in parallel rather than in series. As a result, the springs are not as stretched out, and overall it's a win. Overall, the weight really will levitate, okay? And this is not just hypothetical. If you go to, I encourage you to go to YouTube, search for Braess's paradox. You will see sort of video demonstrations of people building these contraptions and demonstrating the levitation, including some former students of mine who wanted extra credit in my graduate classes. So, all right. So let's sort of circle back and take stock, right? So what have we seen? We have this routing network. We've played around with two toy examples, Braess's paradox, Pigou's example. Price of anarchy happens to be 4/3 in both. And so, you know, I always try to advise my students, right, when doing research, I said, always think about, like, what is the coolest statement that could possibly be true, given what you know so far? Like the coolest statement that you haven't yet falsified, right? Maybe try to prove it, okay? Maybe you'll falsify it and you'll have to revise your guess, but always think about what's like the most general thing that could be true given what you know. So if you're feeling bold, or even maybe like a little delusional, you might take these two networks and say, like, you know what, maybe it's always at most 4/3, right? Always, right? At most 4/3. And the reason that's kind of bold and borderline delusional is that, you know, those of you that study networks know, networks can get really, really complicated. Okay, they could be way bigger than these toy examples. There could be a mess of edges. Who knows what's going on? Who knows what's happens in sort of non-toy examples? But despite the fact that it seems kind of implausible, it's actually true. Okay, so this is one of the results in my thesis, which I did at Cornell with my advisor, Eva Tardos. And so it turns out that no matter how big your network is, no matter how complicated it is, no matter how many origins and destinations you have for traffic, as long as each of the cost functions is of the form ax plus b, okay, so an affine function, ax plus b, both non-negative, that generalizes the 1s, 0s, and x's we've been looking at so far. No matter how complex the network is with affine cost functions, in fact, there is never an increase in commute time more than 33% at equilibrium relative to the best imaginable traffic pattern, okay? So maybe not surprising that self-interested behavior leads you to self-optimal outcomes. Maybe it is surprising that, at least in this case, the outcomes actually aren't as suboptimal as you might have expected. So this is not the time or the place for sort of formal proofs, but maybe let me say a little bit just kind of as a metaphor, right, to maybe give you the spirit of why some result like this might be true. So let me do an analogy with electrical current flowing through networks of resistors, much as you might have studied back in high school physics. Because it turns out you can think about electrical current in a network of resistors as a special case of this routing model. It's the special case in which all of the b terms, the constant terms, are equal to 0. So we're looking at a network where you might have an x over here, you might have a 2x over here, a 4x over here. That 1, the 2, and the 4, those are going to be the resistances. So that's current in an electrical network. And so what are some things we know about that? Well, we know that electrical current you can think of, if you want, as an equilibrium, in the sense that it equalizes the voltage drop across all paths between the two terminals. On the other hand, there's also Thomson's principle, which states we can equally well think of electrical current as minimizing a natural energy function. Okay, so we can think of electrical current not only as equilibria, but also as optimal solutions to a suitable optimization problem. And it turns out in this special case where all of the b terms are 0, it turns out that energy function is actually exactly the objective function we care about here, the average travel time. So in other words, what high school physics tells us is that if all of the b terms are 0, then in fact the price of anarchy is equal to 1. There's actually literally no loss from allowing people to choose their own routes. It's just as good as what you'd get with central control. Now in this model, right, we do have b terms that can be non-zero, and as we've seen, you may have suboptimal equilibria in this case. But it is still true that traffic equilibria can be viewed as minimizing a suitable energy function. It's just that energy function no longer exactly corresponds to the commute time objective function that we care about. But if the functions are affine, it turns out those functions are close to each other. So by virtue of equilibrium traffic exactly optimizing an approximately correct objective function, they are approximately optimizing the objective function we do care about, the average commute time. Okay, so on some kind of basic level, that's the intuition for why a result like this could be true. Okay. All right, so that's enough about routing. Before I move on to the second two case studies, bear with me for a digression, okay? So that result I just showed you, right, I was a grad student at Cornell, and that was going to be one of the key results in my thesis. And you can probably imagine, right, remember when that traffic routing model was from? It was from 1920, okay? And it was very extensively studied in the second half of the 20th century. Hundreds, if not thousands, of papers about that routing model, largely in transportation science. So I was paranoid that I was going to go to Carpenter Library, the engineering library at Cornell, and find in some dusty 40-year-old journal what was supposed to be one of the main results of my thesis, okay? I haven't found such a paper. I didn't find it back then, still haven't found it now. But still, to mitigate my paranoia, I needed to come up with some story, right, some narrative about why for some reason it had to wait till the 21st century for this 4/3 theorem to be proved. And so I want to tell you about the best answer I've come up with. And actually what's funny is the seeds of this answer, I think, were initially planted here at the Institute. Okay, my first visit to the Institute was fall 2002. Okay, so not long after that result came out. Eric Maskin was here on the faculty, and Avi, who was my host, invited me over and introduced me to him. And so Eric sort of just listened very patiently while I talked through these results on the blackboard in his office. And when I finished, he looked at me, he paused for a moment, and he said, "It's a very natural result. I never would have thought to prove it," which was very striking to me at that time. I was like, why not? It's like, it seems like the obvious thing to prove. But why? Why did it seem like the obvious thing to prove for me and not for someone like Eric Maskin? Okay? And the answer connects to NP-completeness, which is also going to be relevant for our second and third case studies. So let me do a detour for a little bit about NP-completeness. Actually, instead, let's talk about maps for a second, okay? So as you know, in maps, countries generally have different colors, right? It should be easy to tell where one country ends and the next one begins. So if you look at a map, different countries are often colored in different colors. And way back in the day when you could actually make a living printing maps, a very relevant question to your production costs was how many different colors of ink do you need to color all the countries in the map so that that property is satisfied, so that adjacent countries do indeed get different colors. Okay? So you can ask that question about any map that you want. North America is not so interesting to ask this question about. So let's turn to Europe, or a part of Europe. Okay, so these are 9 countries in Europe. And we can ask, I will say, for the geography buffs among you, you may complain about the omission of Liechtenstein. It doesn't really change the story, so just please bear with me. So you can ask it about this map. How many colors do you need for that property? Obviously, you can't just use one color, right? That's not going to be enough. Is it possible to color each of these countries red or blue and have the property that any 2 neighboring countries have different colors? No, it's not. And it's not that hard to see why not. You could look at, for example, Germany, the Czech Republic, and Poland, and observe that each of those countries borders the other 2. All right? So even just to color those 3 countries, you're going to need 3 different colors, red, blue, and green. So suppose I gave you red, blue, and green, 3 colors. This is a harder question. Is 3 colors sufficient to color this map without any conflicts, with any 2 neighboring countries having distinct colors? I see some of you have already figured out the answer. So 3 is not enough, it turns out. One way to see this is to focus on Austria, okay? And the countries bordering it, okay? So every country in this picture, other than Poland, borders Austria. Okay, so that's 7 countries. 7 countries form a ring around Austria. And I claim just to color these 7 countries, you're going to need 3 distinct colors. And it's important, right, that there's 7 countries in the ring rather than 6 or 8. If there was an even number, you could alternate red-blue around the ring, and that would be fine. If you have an odd number like 7 and you try to alternate, when you get to the end, you have a parity mismatch and you have a conflict. So you need 3 distinct colors just to color these 7 that surround Austria. Austria, because it borders every single one of those 7 countries, is then going to need a 4th color. Okay? You can color this map in 4 colors. In fact, there's a famous theorem, it's right around its 50th birthday, actually, called the 4-color theorem, which says that you can color any map in at most 4 colors. Okay, so some maps only need 3, some need 4. All right? So the next thing I want to ask is, take this map coloring question. It seems a little tricky. Is this a problem we could imagine solving automatically using a computer program? So computers help us just figure out how many colors are necessary. And again, I planted seeds at the beginning that should make us ask, well, okay, let's think about that. Because Turing told us way back in 1936 that there are going to be problems that are going to be unsolvable by computer, like the halting problem. So maybe this map coloring problem is one of those undecidable problems. But then you think about it a little bit and you're like, yeah, no, it's not. Still not undecidable. You definitely could, in principle, let me go back to the slide. You definitely could, in principle, solve map coloring using a computer, if nothing else, by exhaustive search, okay? Meaning try all possibilities, all right? So in a map with 9 countries, right, if you're trying to color it with 3 colors, that's 3 choices for each of the 9 countries, or 3 to the 9 options, which is about 20,000. So you just run all those options through a computer. That wouldn't take long with 20,000 options. If one of them succeeds, great, you found a 3 coloring. If none of them succeed, well, you tried every possibility, so I guess you need 4. Okay? So how do we feel about that exhaustive search algorithm? Well, the flaws become more obvious if you try to just color a map not with 9 countries, but maybe, for example, the whole globe, okay, all the countries on Earth. So that's ballpark 200 countries. So now we're talking about not 3 to the 9 options, we're talking about 3 to the 200 options. And that's actually a really big number. Okay? That's actually more than the estimated number of atoms in the known universe. Okay? 3 raised to the 200. So in principle, you could try by exhaustive search, but that algorithm would never halt in our or anyone else's lifetime. Okay? So it's not so much that we're worried about map coloring being fundamentally unsolvable. It is solvable in principle. We're worried about it being unsolvable in practice, unsolvable by methods much, much, much faster than exhaustive search. And so the existence of problems like this motivated Cook, Karp, and Levin to develop the theory of NP-completeness, which in some sense is a refinement of Turing's theory of undecidability, two problems that are solvable in principle but appear unsolvable in practice. And I say appear to be unsolvable in practice because that interpretation of NP-completeness rests on an unproven mathematical conjecture, the famous P not equal to NP conjecture, which roughly seems to state something that seems kind of semi-obvious to all of us, which is that solving some kind of tricky problem from scratch should take a lot more time than just verifying someone's work, verifying someone's purported solution. So anyone who's TA'd sort of a math class is sort of familiar with that difference. But yeah, we don't know if that's true in a mathematical sense, okay? Most people believe that it is true, but it's unproven if P is not equal to NP, okay? However, if it is, then this family of NP-complete problems actually are unsolvable in practice, in the sense you can never have an algorithm which is always fast and always correct, okay? So this theory was developed sort of in parallel on both sides of the Iron Curtain in the early 70s by Cook, Karp, and Levin. So actually at the 2021 Stock Conference, we had a session on the 50th anniversary of Cook, Karp, Levin, and that's up on YouTube. We had all three of them participate, sort of very cool. So I encourage you to check that out if you want to see more, okay? So three things I want you to know about NP-complete problems. So thing number one, I sort of already told you. So the interpretation of NP-completeness is that we do not expect there to be algorithms that are always correct and always fast for NP-complete problems. The second thing I want you to know is that they're literally everywhere. Okay, just existing in the world, you encounter NP-complete problems. There's thousands of them. Map coloring, that's an example. Packing your suitcase, that's an example. Scheduling classes in classrooms without any conflicts, that's an example. And there's literally thousands of other NP-complete problems that come up all the time. The third thing I want you to know about NP-completeness is that my field, theoretical computer science, has grown up almost its entire existence, the last 55 years, in the long shadow cast by NP-completeness. Okay, so people who do what I do, people in theoretical computer science, we are accustomed to the idea that we will almost never be able to get what we want, never be able to get always fast, always correct solutions for lots of the problems that we care about. Of course, we've also had to earn a paycheck for the last 55 years, so we've had to find ways to make progress on NP-complete problems even in the face of this intractability, and our field has come up with a rich toolbox for doing so. One of the most common is to use what are called heuristic algorithms. So algorithms which are generally always going to be fast, but will not always be correct. For example, maybe you have a heuristic algorithm for map coloring that always uses at most 4 colors. Sometimes there's a map where actually in hindsight you could have used 3 and the algorithm actually uses 4. So in that sense, it's not always correct, but this is still, if it's fast, a useful algorithm, okay? Always using at most 4 colors to color any map, okay? And so one of the primary ways that we measure the effectiveness of a heuristic algorithm is by measuring how suboptimal the output of that algorithm can be. Okay, how far is it from the ideal optimal solution? Okay, so we use approximation ratios to quantify the suboptimality of heuristic algorithms. And that is exactly the same methodology we are using when we talk about the price of anarchy. It's in a completely different context. We're not talking about the performance of heuristic algorithm for NP-complete problems. We're talking about sort of the quality of equilibria in games, but the mathematical formalism is exactly the same. Okay? So why was it natural for me and my advisor Eva Tardos to ask this question when we encountered Braess's paradox in Pigu's example? It's because, again, our whole careers, we were used to quantifying inefficiency because we couldn't get what we want, because we couldn't have full optimality. Okay? So that's the best story I've got about why that 4/3 theorem had to wait till the 21st century. Let's return to the case studies. Okay? So the next one, I want to talk about a big auction, tens of billions of dollars involved, that ran in the US in 2016 and 2017, and where computer science played a really fundamental role in both its design and our understanding of its performance. Okay? So the auction actually ran, again, a little less than 10 years ago, 2016, 2017. It was authorized by Congress a few years before that in 2012. And the government has been running auctions to sell licenses for wireless spectrum, largely to telecom companies, since roughly the mid-90s. What was really unique about this auction, called the FCC incentive auction, is that not only was it selling licenses to telecom companies for what were going to be sort of new 5G technology, but it was actually also buying back those licenses from their current owners. So for the first time in 2012, spectrum was full. Everything that would have been useful for 5G technology was already accounted for. So this is really a double auction. The government had to both shell out a lot of money to the current owners of licenses, which in this case were over-the-air television broadcasters, and then turn around and run one of the usual forward auctions, where once it had the licenses, it would sell those to the highest bidder. Again, AT&T, Verizon, et cetera. Okay? So that's the FCC incentive auction. It has a reverse auction, where you're actually buying back licenses from the current owner, and then a forward auction, where you're selling those licenses to the highest bidder. I want to tell you a little bit about each of the parts of it. Okay? So designing these auctions, I said, it's tens of billions of dollars, and it's very easy to screw them up, which makes it a very stressful job. Okay? So one famous debacle was in New Zealand back in 1990. In New Zealand's defense, this is before governments had almost any experience using auctions to sell off licenses. And so New Zealand decided at that time, they're like, you know what? We're going to have some new nationwide television stations. Okay, so we're going to open up channels 4 to 13. Okay, and people can buy these licenses to just broadcast across New Zealand. And they decided to sell these 10 licenses via auction, which was a good idea. However, the bad idea was to use a very peculiar kind of auction format known as parallel second price auctions. Okay? So a second price auction is actually a really cool idea if you're just selling one thing. Okay? So in a second price auction, you collect bids, you ask everybody how much would you be willing to pay, like say for this one license that I'm selling. You award it to the highest bidder, but the highest bidder in a second price auction doesn't pay their bid, they pay the highest bid by somebody else. They pay the second highest bid overall. If you're selling just one item, that auction has the extremely cool property that bidders have dominant strategies. Remember, we talked about dominant strategies in Pigu's example, where you have a sort of no-brainer, always optimal strategy. Second price auctions have a dominant strategy, which is just to report your maximum willingness to pay. You can trust the auction to, in effect, shade your bid on your behalf, in hindsight, to give you the best possible price. That's a second price auction for one item, great idea. They decided to sell 10 things by running 10 second price auctions in parallel. Terrible idea. Okay? I don't know why they did this. I can only chalk it up to lack of experience. So they were hoping to make $250 million. So that would be $25 million per channel, per license. Okay? And they didn't even get 15% of that. Okay? They made only $36 million. But boy, man, if you dig into the numbers, so for transparency reasons, right, they were compelled to announce not just kind of the high bids, but also the selling prices, which, remember, in a second price auction is the second highest bid, and also they didn't use a reserve price, okay? So they were compelled to release all of the data about these auctions. To give you one example, there's one of these channels, all right, where the high bid, okay, therefore the winner, was $500,000. And already at this point, you're like, okay, something's gone horribly wrong. They were hoping to make $25 million per license. You're telling me the high bid was $500,000, off by a factor of 50. The second highest bid for that particular license was 6. Okay? Not 6,000, 6. So someone got the right to broadcast nationally across New Zealand on a particular channel for $6. Okay? And again, fast forward to now, US, a couple decades later, you're talking about tens of billions of dollars at stake. Okay, so scary stuff designing these spectrum auctions. So the reverse auction, this is the part where the government is buying back licenses. This was completely new, never been run before. All of this was designed completely from scratch, and computer science was super, super important for the way they decided to solve it. Okay? So they were purchasing back licenses. So they were going to pay off television stations in exchange for their licenses, all right? And they needed to buy back enough licenses to have enough useful spectrum so it would be worth it to run the forward auction. And so they decided early on that they really wanted to clear television channels nationwide. So maybe you'd focus on television stations currently broadcasting on channels 38 to 51, those 14 channels. And maybe you'd say, you know what, let's clear out 10 of these. Okay, so that after the auction, only people are broadcasting on 38 through 41, and 42 through 51 are free to sell in the forward part of the auction. The problem is that when you're sort of looking for sort of television stations willing to sell their license at a reasonable price, you get this very sort of piecemeal buyback, right? There'll be some on channel 47 over here, some on channel 43 over here, some on 51 over here, and that's not directly useful. So it was crucial that the government used its power to actually unilaterally reassign the channel that various stations broadcast on. Okay, so it was not eminent domain. So if you had one of these licenses, you didn't have to sell it. You could refuse to sell it. If you kept your license, it was totally possible that while you were broadcasting on channel 51 before the auction started, you would be forced to start broadcasting on channel 41 after the auction concluded. Okay, so that was an important part of this auction. And so that means, right, so if your target is to clear 10 of the 14 channels between 38 and 51, what is it you got to do? You got to buy back enough licenses from television stations so the ones that remain, okay, the ones that kept their licenses and are still on the air, it needs to be possible to reassign them to television channels so that collectively they only occupy 4 of them, leaving the other 10 clear nationwide. I think a picture will help make this really concrete. So here each circle represents a television station. The area of the circle represents its broadcasting radius, and the color represents the channel. It's not an accident that overlapping circles have distinct colors, because 2 television stations broadcasting on the same frequencies would interfere with each other. Okay, so it's important that overlapping circles have different colors. So here we're using 3 different channels, and it's easy to see that that's necessary, because here's 3 stations that are mutually overlapping. So you would need to use 3 different channels just to keep all 3 of these stations on the air. But some of these licenses are being purchased back, okay, by the government. And so maybe like that big blue one in the upper right, maybe their license gets bought and they get taken off the air. Seems like it doesn't help, right? Still using 3 different channels. But remember, we can reassign, we can recolor. And by the suitable reassignment of television stations to channels, we can now actually get all of these stations on the air using only 2 different channels. Okay? Notice we're using the fact that this is an even cycle of overlapping stations rather than odd to get the 2 coloring. Okay? All right. So I hope at this point, right, you kind of have like a little bit of a deja vu moment. Like, weren't we talking about this exact problem, like, I don't know, 15 minutes ago? And that's correct. This is like literally basically the map coloring problem. And seeing that, you now should have some questions for me, right? You should be like, okay, so let me get this straight, all right? There's lots of NP-complete problems, and we can't solve them, all right? They're unsolvable in practice. You said that. You said map coloring was one of them, and now you're telling me that this auction involving tens of billions of dollars was solving map coloring problems. Like, how does all that work out? How is that possible? And the answer is, it was not easy, okay? It was a major engineering effort, but indeed, the FCC incentive auction did solve NP-complete problems fairly reliably, even fairly large-scale ones, pretty quickly. Okay, so there was an entire team led by Kevin Leighton Brown, who's a computer science professor at University of British Columbia. There was an entire team responsible for doing this, okay? And so the approach was to stand on the shoulders of work in what's called SAT solvers. SAT here stands for satisfiability. So satisfiability, that's a problem where you're given sort of a long logical formula, and you want to know whether it's possible to assign its variables to true and false so that you can satisfy the entire assignment. Satisfiability turns out to have a lot of pretty valuable applications. So hundreds of really smart people have devoted a lot of effort into having better and better heuristic SAT solving algorithms over the years. So Leighton Brown's team, the first thing they did is they say, let's stand on the shoulders of today's SAT solvers. Let's encode map coloring at a satisfiability problem. It turned out the off-the-shelf SAT solvers still weren't quite good enough for the performance that they needed. So the next thing they did is something you often do when you're solving NP-complete problems in practice, which is you bake in some of the domain knowledge that you have. That is, you stop worrying about trying to solve all the instances you might ever encounter quickly, and you say, let's just worry about solving the instances that are going to be relevant to our application. Okay, let's specialize to the instances we expect to see. And in the FCC incentive auction, because they knew all of the television stations involved up front, and they knew all of their broadcasting radii and who interfered with whom, that was a ton of domain knowledge they could sort of bake in to their heuristic satisfiability algorithms. And that was crucial to their ultimate performance. Really impressive what they got at the end. They were solving satisfiability problems with tens of thousands of variables, hundreds of thousands of constraints. So I would say that's like medium to large kind of satisfiability problems. And they were usually doing it in less than a second. It took a lot of work, but they did get there. So that's why the FCC incentive auction was able to be successful, despite the fact there was NP-complete problems as part of it. Okay? And I hope the high-level takeaway here is clear, namely that but for cutting-edge techniques in computer science for coping with NP-completeness in practice, the government literally could not have run this auction format. They literally would have had to do something else, probably something economically inferior because of the computational challenges involved. Okay. All right, so let me actually skip ahead to the third case study. This one will be short. And I want to circle back to where we started, which was to Nash's universality theorem. Okay, so remember, Nash proved any strategic situation, doesn't matter who the actors are, doesn't matter what they can do, doesn't matter what they want, there's guaranteed to be an equilibrium point. There's guaranteed to be a Nash equilibrium. I said this gave game theorists and economic analysts everything they could possibly want. Okay, they don't have to worry about the details of their game. They know there's going to be an equilibrium they can use to reason about what might happen in that strategic situation. Okay. Well, but you might want a little bit more than that, right? If you think about it, a lot of the interpretations of a Nash equilibrium presuppose that somebody, maybe the players themselves, maybe some third party, like some kind of mediator, but somebody, some boundedly rational actor, somehow figures out what the equilibrium is, what actions players should in fact be taking. And so it would be nice if we had a constructive version of Nash's theorem, which didn't just offer us this abstract promise that there always exists somewhere out there in the world, some equilibrium point, but gives us a principled way to deduce what it actually is. Right? Ideally, a fast algorithm, maybe even, for computing a Nash equilibrium of a game. And Nash actually proved this in two different ways, but both are using fixed point theorems, and they're non-constructive, at least in the sense that computer scientists would mean they don't lead to efficient algorithms. So the usual proofs of Nash's theorem do not seem to yield a constructive version. So this was an open question for a long time. Really, ever since Nash's theorem, people wondered, could you have some more efficient, some more constructive version of Nash's theorem without losing, without compromising on its universality? And lots of smart people worked on it. No one could come up with efficient algorithms. And when that happens, you start wondering if maybe no efficient algorithm could exist. And so once you start thinking that way, like, what have I told you? I've told you, well, there are these thousands of NP-complete problems. You bump into them sort of on every street corner, and we don't seem to be able to solve them. So the natural reaction at this point would be like, oh, maybe computing a Nash equilibrium is like yet another one of these NP-complete problems. Okay? And that's the right thought. On a technical level, it's not quite the right statement. And this was pointed out by Nimrod Megiddo some time ago, where he said, look, there's this like type checking error between the notion of NP-completeness and this problem of computing a Nash equilibrium. NP-complete problems, like think about map color, right? You're asking like, can you get away with 3 colors or not? And the answer might be yes, the answer might be no. Satisfiability, same thing. You're like, can you or can you not assign true or false to these variables to satisfy all these constraints, to satisfy this formula? Answer might be yes, answer might be no. And this is a signature of NP-complete problems. They're yes-no questions where you generally are trying to figure out which one the answer is. What's the yes-no question when we pursue a constructive version of Nash's theorem? We're not asking, is there a Nash equilibrium or not? Because we know the answer. The answer is yes. That's exactly what Nash's theorem tells us. So it's a sort of more subtle kind of intractability where this object that we know is out there is somehow eluding our grasp. So the hardness is in the search for the objects that we know exists, not in the classification of whether or not it exists. So that was Megiddo's point. And so Christos Papadimitriou then suggested a way forward, which he said, well, okay, agreed. we should be proving a different statement than NP-completeness, but maybe we can at least prove that computing a Nash equilibrium is at least as difficult as finding any other object which is similarly proved by existence through a fixed point theorem. Okay? So maybe the Nash equilibrium is as hard as anything that's guaranteed to exist using a fixed point argument. So technically what he proposed, what he conjectured that computing a Nash equilibrium is complete not for the complexity class NP, but for a smaller class he called PPAD. So he proposed proving a mathematically weaker statement that nonetheless has similar interpretations. So under a strengthened analog of the P not equal to NP conjecture, a P not equal to PPAD conjecture, if you could prove PPAD completeness of Nash equilibria, that would explain why there's no constructive algorithm known. Okay? You might be wondering about the alphabet soup. So allegedly this stands for polynomial parity argument directed version. Maybe that's what it stands for, but Krista swears to me that he didn't realize that this complexity class name was a subsequence of his last name, but if you believe that, I have a bridge to sell you. So, turned out to be a very prescient definition and conjecture. Okay, it took a while, it took over a decade, and it took some very difficult proofs. But about 20 years ago, a little less than 20 years ago, it was indeed proved that computing a Nash equilibrium is PPAD complete. Daskalakis, Goldberg, Papamuchu, Chen, Deng, and Tang. And again, what is this? This is an explanation made possible by the language of complexity theory, an explanation about why, for the last 75 years, we have not had any constructive version of Nash's theorem. It seems to have universality. You must give up on efficiency. You cannot have both at the same time. Okay? So wrapping up, I've given you, I hope, a representative, but definitely not exhaustive list of interesting things that are happening at the boundary of computer science and economics. And I want to emphasize this is now a super, super vibrant research community. Every year there are multiple big conferences that are devoted solely to research happening at the interface of these two fields. And I also want to emphasize that the sort of flow of ideas is really going in both directions in a very healthy way. Initially, at the start of this century, computer scientists started learning about game theory and economics because we needed it. Okay? Because the new generations of computer science applications coming out, enabled, for example, by the internet and its commercialization, the new generation of technologies needed game-theoretic or economic reasoning just to faithfully model what was going on. Okay, so as computer scientists, we recognized we needed these new toolboxes to make progress on our applications. We saw an example of routing and communication networks, things I haven't mentioned. So for example, real-time auctions for online advertising, really major effort between computer science and economics, mostly in the 2000s. Honestly, even today, companies like Google and Meta make most of their revenue from auctions of this form. And then more recently, in the development of blockchain protocols, it's also super crucial you get the incentives and the economics right if you want those to perform well. Okay, it also goes in the opposite direction. Computer science has a tremendous amount to offer economics and game theory. I'd say two big categories. So first of all, articulating when and why things are difficult, so articulating barriers. And secondly, offering a toolbox for ways of compromising in a principled way to evade those barriers. So on the compromise side, we saw examples with Approximation, talking about the price of anarchy. We saw examples of fast heuristics for tackling NP-hard problems in practice. And on the barrier side, we saw how PPAD completeness gives us the right vocabulary to explain the absence of a constructive and universal version of Nash's theorem. But really, if you take away just sort of one thing from today's talk, I hope it's just the excitement that I at least feel about the interdisciplinary work that's been going on in this area for the past 25 years. I'm completely confident the next 25 years are going to be just as fun and just as exciting. So I'll stop there. Thanks very much. And I've been told that there's a microphone going around, so if you'd like to ask a question for the folks on Zoom, please wait for the microphone.
Raise your hand.
So I'm interested in your work on transaction key mechanism design, and I know you're responsible for the EIP 1559 protocol. I was wondering if you're familiar with Weinberg's paper on off-chain influence proofness, and what your thoughts are on the limitations of the current protocol and how it might be improved upon.
Yep, great, good question. So to clarify, I was responsible for the first analysis of EIP 1559, not its design. Yeah, I'm familiar with that paper. I sort of a general audience, so I don't want to go like too far into the weeds. But let me just give a short answer. I'd say a major modeling decision is whether you want to think of the block producer as itself being Bayesian versus like, having some kind of knowledge about, people's likely valuations versus not. And I think of, this isn't articulated explicitly, but I think of the original EIP 1559 design as kind of having an ex post mentality. So not wanting to look at Bayes-Nash equilibria, really wanting to look at, or having, not wanting to bake assumptions about a prior kind of into how it works. And so that to me is the big difference. So like, I think that's a shift in that paper where you say, let's assume that actually the block producers themselves are Bayesian, would be willing to run sort of an off-chain Bayesian optimal auction. And then that potentially changes the equation about, what transaction fee mechanism you'd want to use. Thanks for the question. There's a couple down here, so.
Down here.
This is just an observation. I want to hear thoughts around it. So this NP-complete problems, right, like you mentioned, and well known that to solve them, use heuristics and so forth. And with all this advent in Gen AI, the semantic searching, all those things, would it provide a way to search through heuristically in a more deterministic fashions, solutions to these problems, which otherwise explode that, a mechanical way of making these heuristic optimizations?
Yeah, let me know if this answer doesn't quite answer your question, but certainly one thing which machine learning has been, having an impact on lots of fields, as we all know. And certainly it's still, I'd say, fairly early, but I'd say there's some promising early experiments trying to just use machine learning techniques to learn better heuristics than people have come up with, including for NP hard problems, like for the traveling salesman problem. I think a lot of that is going to depend on whether you're happy to have an algorithm, which works well on a particular family of instances versus an algorithm which is ready for anything. So I think, I'm not saying it's impossible, but I think using machine learning to train an algorithm, a heuristic algorithm is kind of ready for anything. That I think could be elusive, but training one which does well on a fairly stable family. So say you have a company and you're solving like similar instances of an optimization problem over and over again. There, I think there is a lot of promise for using machine learning to just kind of figure out what is going to generally do well on that distribution of problems. Okay. Great.
Thanks. I'm a historian, so I'm listening to you in a somewhat different perspective.
Great, great.
But you opened the door for me by pointing, for example, to Pigot or other historical roots, and then raised the question about, in your conversation with Maskin, about why didn't somebody ask this question before? Now, I'm not sure that I actually get exactly what it is that you're asking that about, but within a larger framework and in the way in which you fill in a lot of the material here, it seems to me that C.S. Peirce deals with a lot of this and struggles. So in his formalization of logic, and specifically in the introduction of the idea of abduction, the Peirce struggles with this, and while under other frameworks or under other categories, he has some things to contribute to formalization. He struggles with the question of formalization about abduction, but for him, abduction is the logic that covers, for example, approximation and heuristics, and especially when you reduce the frame, and so in your, is it a yes or no question, and then so we say it's a yes question, and then then the subsequent question or the next level of address is going to be about, so what exactly within that domain do we need to ask, and how do we locate a position in the domain for asking the next question? That's exactly what he's talking about. So if you haven't thought of looking in his collected papers, it's worth a shot.
All right. Thank you for the recommendation. Fantastic.
Oh, you not answered the question?
That's it. It's all you.
So the question I want to ask is that at the intersection of computer science and game theory, and if you take the human problem that we want to solve, so which is a bigger challenge, translating a human problem into the framework or designing an algorithm to solve a translated problem?
That's a great question. I would say they're different skills in a way. And I think, in textbooks and classes, even to some degree in research, a lot of the focus is on take the problem as given and now come up with better solutions. And you're absolutely right that, I mean, if you try to apply these skills, if you try to go outside of the ivory tower, and help people, whether it's in government or in industry or whatever, a lot of that conversation is sort of what exactly is the problem, or what are the important parts that we need to keep and the unimportant parts that we can throw away. And that itself is a fantastic skill. And I struggle with how to incorporate more teaching of that skill in the classes that I teach. It's not the easiest. I think the easiest way to get it is literally just by talking to practitioners and seeing the gaps between where the theory ends and where their needs begin. Like a great example would be even in those spectrum auctions, right? So in kind of the whole theory of auctions, like they do the setup and they're just kind of like there are M items for sale, and it's left unaddressed like how were those items chosen? And like in practice, like including in the example I mentioned here, there's a lot of different ways you could structure the market and like what's being sold. So it's absolutely, it's a little elusive to capture in a lot of the mathematical models that we work with, but in practical terms, it's a very, very important complementary skill. Yeah, it's a great point.
Thanks for the great talk. So, so like going back to the Braess paradox, right? Like the building that extra road made life like really worse than the optimal. I don't know. Do you know of like a conversation that has happened somewhere that was like, we will not build this road because, that's why life is going to be good, or we won't build this product because that will just make life bad for the company or something like that?
Yeah. So I mean, it does surface into. So like, for example, there's a New York Times article, I think it was ballpark 1990, where the headline was, "What if we closed 42nd Street and nobody noticed?" And they're talking about Braess's paradox. I think in practice, the way this gets avoided is I think just any change I think there's just good simulation software. So for any tweak, like you can imagine people asking the question, like, what's going to happen if we increase the speed limit from 40 to 45? Will it make things better or worse? And so I think if you're talking about like serious transportation engineers, they have software to carry out the simulations. And so they would kind of catch empirically, hopefully, one of these paradoxes if it was about to happen. Interestingly, though, I mean, another chapter of my thesis kind of uses NP-completeness and complexity theory to kind of show that Braess's paradox can be deeply hidden. It's not always so simple that there's like a single edge whose removal would fix everything. Sometimes it's like this very complicated kind of well-hidden subset of edges where if you could only find that back door, all of a sudden things would be much better, but it can be computationally elusive to find it. That's probably more of a theoretical result, but as far as like local changes, I would say in practice it's a simulation solution. Yeah.
Hi. You talked about two different extremes in terms of how either every person is looking out for themselves in a Nash equilibrium, or maybe there's someone who's looking out for everyone at the same time and trying to find the optimal solution. Has there been any work on trying to look at subsets of this, or maybe let the people decide who they want to be in equilibrium, who they want to cooperate with, or things like this at multiple levels of scale? How might this go about? For instance, the Braess paradox, two people might decide, okay, we are going to work as a unit and switch, every other day that we're going to go in these spots, and they might.
Yeah, that's a good question. And it's funny because actually, if you go back to the 1944 book, von Neumann and Morgenstern, a huge chunk of that book is actually thinking about sort of coalition formation. And it's somehow, It's a little bit lost to the sands of time, honestly, for the large part now. But at the time, that was a big part of his thinking. I'd say in the routing model specifically, it's pretty easy to extend the model in different ways, and people have probed it. So, if you imagine, just a lot of different variations. Like imagine there's a certain subset of the traffic that's sort of a coalition. Imagine some of the traffic, gets sort of routed using kind of, Waze, like Waze routes part of it in some way. How does the rest respond? If in that case, like how should Waze route people? So that's a model where, one thing that's nice about that model is it's simple enough. There's a lot of different ways to add bells and whistles. As far as how to just treat that generically, it's not obvious to me that there's a helpful way to think about that just generically across all games. It may be somewhat application specific, the most meaningful way to do that. So. Looks like there's one more back there.
Hi, I'm also a historian. Thank you for your talk. I was wondering whether you'd like to say something, given the sweeping historical overview, about both the tension and synergy between theoretical inquiry and applications, be they business or policy, in both fields and in the intersection of the two fields, a different conjuncture.
Yeah, let's see. Trying to think if I have anything new to say on the topic. I mean, I will say, so, yeah, it's a good question. I mean, game theory is an interesting one because the origins of game theory, there was a lot of, it would seem clear that von Neumann had various policy recommendations in mind coming from his early game theory work. I would say, the field of game theory these days is less like that. The field of game theory these days feels fairly more like a branch of pure math. I'd say, theoretical computer science is another really interesting one. One of the things that's really fun about theoretical computer science is you kind of get to, in many cases, be simultaneously working on kind of deep scientific questions, but also doing things that are fairly directly helpful for people trying to build things or make decisions around real systems. Actually, the slides that I skipped because of the time was exactly this point, where it turns out there was sort of a long time this folklore belief around types of spectrum auctions and whether or not they had to be complicated, like whether or not they had to allow bidders to bid not only on individual licenses, but also on packages of licenses. And there was sort of a folklore belief among economists that kind of complexity was required. And it actually turns out that a fairly obscure part of complexity theory called non-deterministic communication complexity, which I think you would only work on if you were focused on the computational mysteries of the universe and ignoring kind of practical applications. But that's actually exactly the right concept to make precise the economist's folklore belief about necessary complexity of spectrum auctions in certain contexts. So I'd say that's, I'm just giving you little kind of anecdotes around your question, but that seemed like a good note to end on. Theory of computer science, I kind of feel like we get to have it both ways, right? If we want to just really sort of focus on sort of deep math, but then like very closely adjacent to that are kind of implications of that math for real computation and real systems. All right. Thanks again, everyone.